This is 4.1 exponential functions, part 1. So this first slide right here is having us enter in a base of 10 and then an exponent of 2.6. And notice as we go down the line, all the bases are 10, right? And just the exponent increases. And so let's just go ahead and enter that into the calculator. Now looking at the calculator, oh, I had some previous work there. Let me get. Okay, so looking at the calculator over here, on the right, we'd put in the base of 10. And then look on this calculator on the left just so I can show you where. We're going to press this button right here to get that exponent box. So going back to my calculator on the right. And then it opens up the box for us to input whatever the exponent is. So that's what we'll do for all of these. Press execute, and boom, you have your answer. So we're just going to approximate to the nearest whole number. So 398 for this first one. And then let me input the rest of these into the calculator. So this actually reflects the Richter scale. If an earthquake is a 4.2 on the Richter scale, then the intensity in the ground is 15,848 versus if it's a 6.5 on the scale, which might not seem like a huge increase, right? But look at the increase in the intensity. So noticing that there's a huge growth when you're dealing with exponential growth. So just showing that that's a real life example of how we use exponential functions. So looking here, it says an exponential function is a function of the form y equals a times b up to the x power, where a is not equal to 0, b is greater than 0, and b cannot equal 1. And the exponent must be a variable. Right? And that's important to understand because we've dealt with functions before where we've had exponents. In a quadratic function, we've seen x squared in the function, right? So there's an exponent, but notice that in that example, the exponent was the base. So now we're looking for the variable was the base, but now we're looking for the exponent to be the variable. So that's going to be the difference with these functions. Okay, so your questions like this, you will just go to your calculator, input your base, use that caret key, and then input whatever they're asking for the exponent. So they're showing you a value in exponential form, and they're asking you to write it in standard form like we did on that first slide with examples of the Richter scale. So square root of 6, and then we execute it. And it does not specify here how many decimal places to take it out to. So just make sure you pay attention to that in your homework. It'll specify how many decimal places or which decimal place to round it to. But here we'll just go ahead and take it out to 3. So I'm going to put 80.551. So this slide reiterates that the base must be greater than 0 and not equal to 1, right? So let's just talk briefly about that. Think about this. If the base is 0, regardless of what my exponent is, this is my x, right? But regardless of what that would be, my answer is still going to be equal to 0, because 0 to the 5th power, 0 times itself 5 times, it's still going to be 0. 0 to the 100th power, right? So we would not get that exponential function that we're seeing in the slide right here. And then it can't be equal to 1 because, again, 1 to whatever power It doesn't matter what we put there. It's going to give me 1. 1 to the 8th power is 1. 1 to the 2nd power is 1. And so that's why it has to be greater than 0 and also not equal to 1. Oh, and then also just consider on the flip side of that, if it was less than 0, now I have this negative value, and depending on if I'm raising it to an even power or an odd power, I'm either going to get a negative output or positive output. So base has to be greater than 0 and not equal to 1. So notice that here in these functions, as my base increases, I'm still passing through 0, 1 right here, right? And there's a horizontal asymptote at y equals 0. Okay, so here's a graph that just shows a real life example of an exponential function, right? So the way that the population of the Earth grew, look, in 1804 we were at 1 billion, and then by 1927 we were at 2 billion. So we doubled, but we didn't have to wait another 100 plus years to double again. By 1974, we had already doubled. So that would be a perfect example of exponential growth. So I want to remind you that you have done slides like this before. You have not done them with exponential functions yet, but you have done them. You're simply going to go to your calculator and we'll go to graph it. So we'll press 5 to get that graph. And then my function is 4 up to the x power. So I'd put 4 in there and then raised up to the x power. And that's it. I'm going to graph it. And look, sure enough, it passes through 0, 1, and I have this horizontal asymptote at y equals 0. Then they're asking, so that would be the portion of my question that I'm looking down for the multiple choice where I'm trying to locate my graph. So let's go ahead and compare those pictures. It's definitely not C, right? Definitely not D. A and B are both passing through 0, 1. So let's get some of these points graphed, which maybe we should have done first, right? Since it's asking us the table, but let's go ahead and go to the table. So I'm going to go back to the menu. I'm going to press 7 to get into my table. I go to the table, notice that it starts at 1 and I need the table to start at -2. So I'm going to exit out. And here in this screen, I'll press F5 for set. And I'm going to start it at -2 because that's the first one I need. It can go to 5, that's fine. I only need till 2. And then yes, I want it to go by 1s. So let's go back to our table. Now notice that it shows me a decimal, right? I can arrow over to the right. Oops, went too far. I can arrow over to the right and it's not showing me as a fraction. Let's see if I could change that. There we go. Okay, I pressed F to D. Usually when you arrow to the right, in my experience, it's showing you a fraction. Okay, so it shows us the fraction 1/16. Then I say, okay, 1/16, let me write that in. Let me fill in the rest of these from the table. Okay, we got the rest of our table filled in. So after you filled out your table, now when I look back at the graphs, I can definitely use this information to eliminate the one that it's not between A and B. So they both pass through 0, 1, right? But look at where 1 is. When x is 1, y is 4. So I'm going to look at that point. Okay, when x is 1, y is 4. Okay, that does look like 1, 4. Let's see here. When x is 1, y is looking like it's closer to 2, right? But that's still a little questionable. So then I go to this point, 2, 16. So when x is 2, y should be 16. Okay, that matches, right? That's about 16. When x is 2 over here, y is only about 4. So we know that it's not that one, so A would be my answer. Okay, going back up to the top, they want to know the domain. So remember, the domain is all the possible x's we can have in this function. So going from left to right, I can see that I'm going to start at negative infinity. And I would keep, as I move to the right, as I'm moving to the right, I'm raising up, right? But I'm going further and further to the right. So I would just keep going and going and going and going. So it would be positive infinity. And then for my range, remember there's that horizontal asymptote. So we see that this is where we actually begin our points, right? So I'm not including it though. So it would begin at 0. And then we see that it continues upward without bounds. So to infinity. My horizontal asymptote, unless this graph has been shifted upward any, then we're going to have that horizontal asymptote at y equals 0. So before we look at the next one, let's just talk about these exponential functions, but the difference of when we have a base that is greater than 1, like in this one on the right, our base is greater than 1, versus a base that is less than 1. So remember, it has to be greater than 0, the base, and it can't be 1, but there's values in between 0 and 1, right? Like fractions. And so that would be equivalent when we have a base that's a fraction to having this negative exponent. Remember that when we had like a negative exponent, how we could put in the denominator, right? We could take the base and put it in the denominator, and then that exponent would be positive. And so that's what we're seeing there. But when you have a base that is less than 1, like this example with 1/2 up to the x power, you have a function that shows decay, right? So less than 1, then we have a downward sloping exponential function. A base that's greater than 1, we have I said sloping, but an increasing, right, exponential function. So here's another slide that shows the base with it being less than 1, and then a base where it's more than 1. The one on the left is the base that's greater than 1, right? And then we see the exponential function on the right where we have the base that's less than 1. Notice that they're both one-to-one functions. They both have a y-intercept of 0, 1. Neither of them have x-intercepts because we have that horizontal asymptote at y equals 0. They both have a domain of negative infinity to infinity and a range of 0 to infinity, not including 0. So now let's do this one. 3/4 raised to the x power. So we're going to get our calculator. I'm going to go back out to where I enter it into my table. So 3/4 raised to x. And notice I put it in parentheses, so it's the entire 3/4 is the base, right? It's not 3 raised up to the x power over 4. It's 3 over 4, and then that being the base raised up to the x power. So let's see how that table looks. Okay, again, it's giving me some funky decimals for my y, so I'm going to arrow over to the right, and I can see my fractions in the bottom right corner. So 16/9, 4/3, 0, 1, there goes our x-intercept, 1 3/4, and then 2 9/16. So I'm going to go ahead and fill in my table. Okay, so table's filled in. Let's go ahead and see how that looks. On the graph, going back to my menu, graph, draw it out. Okay, so remember, we have the horizontal asymptote at y equals 0, and then we know it's going to pass through 0, 1, right? Because it's just that basic exponential function. Like I don't have like 3/4 raised to the x power and then on the outside plus 5 or anything. So it hasn't been shifted anywhere. So looking at my graphs, I'm like, okay, well, C and D don't even pass through 0, 1, right? So those are gone. Then A and B both pass through 0, 1, but let's look at some of the other values. So I'm actually going to look at -1 4/3. So I'm like, okay, when I look at that, I'm looking for -1 4/3. So 4/3 would be 1 1/3. So when I look at -1 on A, I'm like, okay, that could be 1 1/3. And I look at B and I'm like, okay, that could also be 1 1/3 for -1, right? So I'm looking at these points right here. So then I could look at -2. Now you can choose any 2 points on there, or you could choose any point and then confirm with the second point. So when I look at -2, I'm like, okay, this one would be 16/9, so that's approximately 1.7. I could get this off my table, 1.8. And that's not very close to 2. That's halfway. This point right here is halfway between 1 and 2, maybe slightly over, but this is pretty close to 2. So that would be my answer. So you could use process of elimination to get rid of the ones that don't even pass through the y-intercept, but then you're going to have to use some other points to eliminate any others. So we're going to graph these and see which of these functions produce that graph on the right. I could eliminate some. Now, if you're not, remembering how to eliminate those, then that's fine. You can graph them. But if you're able to eliminate them, that makes it a little bit easier. So notice that on all of these, my base is 4, right? Some of them, it has a negative in front of it, but it's not grouped with the 4. So it's not -4 raised to whatever power. It's negative and then 4 raised to that power. So remember that when I had just the basic, grab my pen. When I had the basic whole number that greater than 1, right? So we said if we had a number greater than 1 raised to an x power, then it was going to look like this. So I can eliminate that. And then if you remember when we were doing transformations, so when we were moving our graphs up or down or left or right, depending on if the values that were being added and subtracted were grouped in with my x's, it would move left and right, and it would do opposite of what we think it would do. And then if it wasn't grouped with my x's, then it would affect the y's. It would move up and down, right? And then we had the negative symbol in front, which would flip it and all of that good stuff. So looking at that, I'm like, well, I can eliminate this one as well too, because this would flip it y-axis because it's not grouped in with the x, right? It's out in front, so it's going to be, or all the y's are going to be reflected, so I could get rid of that one. This one right here would be that same graph. This third one would be that same graph up top. This number is not grouped in with my x and the exponent, so it would shift my graph down 1. We can get rid of this graph too. That is grouped in with the x's, so it would be that same graph like this, but it would be shifted to the right 1 unit, right? This one, oh, I'm sorry, that's this one right here that would be shifted to the right 1 unit because we subtracted 1. This one would be shifted to the left because it's a positive 1, but then it would be reflected. Like, you can really get down into all of them. This one right here would affect the y's, but then it also would be reflected. There's a lot of stuff going on in there, right? But remember, the one that we want and the one that we would graph and see the graph that we have to the right is this one. It passes through that 0, 1. And remember, this is equivalent to 1/4 to the positive x. And look, sure enough, that would flip it over the y-axis. So a couple of things, I would say graph it, graph it, graph it. Graph them, but if you do remember transformations, then most definitely, eliminate the ones that you can. But I would still graph the ones that you have remaining because you might have been mistaken and eliminated something. I think on one of these, I said it was going to reflect over the y-axis, and I meant the x-axis. So just make sure that you're graphing it and just confirming what you're remembering from transformations. So it ends up being y equals 4 to the negative x, which is also y equals 1/4 to the x power. So same thing. Nope, this one has the answer on it. So pretend like you don't see the answer. So it says the graph of an exponential function is given. Select the function for the graph. Same thing. You're going to, you can graph all of these and see which one produces this graph. Now, you can use process of elimination if you remember transformations. This means that it would be the graph that we're looking at, since that one is 3 to the x power, and it would be shifted. It's not grouped in with my x's, so it's affecting my y's. It would be shifted down 1 unit. And so it looks something like this. Okay, so once you graph that, you'd be able to see, okay, that's not passing through 0, 1. This one right here is grouped with the x's, right? So it's going to affect that negative -1 is going to affect my x's, and remember it does the opposite, so it would move to the right 1 unit, so we'd see something like this. Okay, and then that last one, it's affecting the x, and it's negative in front of the x, so it would be a reflection upon the y-axis, so something like this. Okay, so when you graph those, all of those should hopefully tell you, nope, that's not it. That very first one, 3 to the x power, gives you that one.